we actually also keep track of the derivation. So the derivation in that context basically means why we think something is vulnerable. So we not only say to the users, hey, this is vulnerable, but we also show them basically the flow that we extracted and why we think this is vulnerable. So since we know this derivation, and we can also basically query the analyzer multiple times after maybe we change something in the code, what we can actually do is we can maybe try to filter out the irrelevant parts in the code. And after we do it, maybe we can ask the analyzer again, hey, do you still find the vulnerability? And if yes, okay, maybe those things that we just removed, they were indeed irrelevant.
You are listening to The Secure Developer, where we speak to industry leaders and experts about the past, present, and future of DevSecOps and AI security. We aim to help you bring developers and security together to build secure applications while moving fast and having fun. This podcast is brought to you by Snyk. Snyk's developer security platform helps developers build secure applications without slowing down. Snyk makes it easy to find and fix vulnerabilities in code, open source dependencies, containers, and infrastructure as code, all while providing actionable security insights and administration capabilities. To learn more, visit snyk.io/TSD.
Hello and welcome to another episode of The Secure Developer. I'm super excited to be back with you today. It's Danny Allen, I'm the CTO of Snyk, and today I have a very special guest. I am joined by Berkay Berabi, who is one of our AI researchers here at Snyk. He's been with us for 4 years and has been very involved in a very new research area that we have published and are patenting around CodeReduce. So we're going to get into that. But first of all, maybe Berkay, if you can just introduce yourself for the audience.
Yes, sure. So hello everyone. I am Berkay. I'm very happy to be here today. Thanks for having me. And I have studied computer science and mostly AI and machine learning. And then I joined Snyk, and I have been here in the machine learning team for around 4 years by now. I worked on a bunch of things, and we will talk about those today.
I'm interested how you got into AI, Berkay. Was it something you were always interested in even before you went to school? Or was it something as you were going to school that, hey, this is fascinating, this is where the world is going?
No, actually, it hasn't been not always the case. Actually, I studied electrical engineering in the bachelor's, and I was always into engineering, maths, and physics, but actually not really computer science. So I actually learned programming for the first time when I was 20. But I did electrical engineering. When deciding on the master's, I actually realized I am not really that interested in electrical engineering. And then I realized I'm actually more interested into programming, and this AI hype was about to start back then. Then I said, okay, maybe I should switch to computer science. And then in the master's, I applied to a computer science program. And then, I did my master's in AI.
Well, that is the perfect place to do it, because I know that you said that AI is hype, and it is true. We hear an awful lot about AI and machine learning, but it is changing the world, and especially the software world. Everyone's role. I always say if I could use AI to take control of my calendar and make myself more productive, I would. But I know even here at Snyk, we're using now machine learning and chatbots to make product more productive, everyone within the organization. So it's a very big thing. And I want to talk today specifically about CodeReduce. This is this project that you've been working on for a while now, and it has to do with generating fixes. So maybe we can start with understanding what it is that we're actually fixing, vulnerabilities. So let's start by just sharing with the audience a little bit about the discovery of vulnerabilities and how that takes place, because if I'm not mistaken, we use machine learning for that as well. Is that correct?
Yes, that's correct.
Maybe you can just share how we discover vulnerabilities and how we use machine learning to do that.
Mm-hmm. Yes, sure. So just maybe as a concept, so what's a vulnerability? So basically, it's very easy to write an application, but then the security complications arise because, like, for even the most basic thing, you actually need an input from the user, right? And you actually use that input from the user, and then you do some computations in the backend, and this can basically bring a lot of complications. So, for example, if you search for someone in a web application, like in Facebook, I don't know, you type a name, and that name actually goes into the database. So I could also write, for example, some SQL query in there that will be malicious, and then that will be executed. So all that kinds of concerns are basically not valid when you are prototyping, developing something, but as long as you have a product, of course, that's one of the most important things. And what we do, our software, Snyk Code Analyzer, we basically developed a static analyzer that can analyze your code, analyze the code of the customers, and then can report all these issues where an attacker or a malicious user could actually do some harm.
We tend to think of inputs as filling out data in a form, but it could be a query string, it could be a cookie, it could be an HTTP header. There's lots of ways to get that input into the application, isn't there?
Yes, exactly. Definitely.
Yeah. So if that is malicious and something bad happens, that is not good. And so how do we go about looking for that type of malicious activity or when things aren't correctly validated? How does that work?
Yes. So, of course, like there are lots of enterprises, you have lots of code, right? This is basically not something that you could basically, monitor manually and all that stuff. Of course, when something is down, like, maybe an attacker can manage to drop your database, then you realize it. But at that point, it's also too late, right? Because probably they also have extracted all the information. So that's why we have this Snyk code, and it can actually do all this analyzing for you. And then you can go over the vulnerabilities, but it is still a manual process to understand the vulnerabilities and actually fix them, unless you are using AI also for this.
How do we identify the vulnerability? Let's start with that, because that's the first step. You need to first identify the vulnerability, and then we want to, we'll get into it, reduce the code.
Yes.
But how do we identify the vulnerability itself?
Yes. And for that, we use a hybrid approach. We call this also hybrid AI. And what happens there, basically, of course, we have some logical rules that basically define certain vulnerable patterns in the code, so in the programs. Things like, okay, this is a user input. Now it goes through these functions, and actually none of these functions apply proper checks or proper sanitization. And then at the end, it goes into this vulnerable or dangerous function where it is used without sanitized. So these patterns are basically written by the security analysts. But of course, this is a very complex thing because you have to write those patterns for every vulnerability for every different kind of case, right? So this is like a good approach, but it's not scalable. And that's why we also use on top of this machine learning to make this approach more scalable and more accurate. So for example, we use machine learning to analyze whether something is really dangerous, whether it is really a user input or whether it's a false positive or not. So we basically combine these logic with the AI to improve the accuracy and also to improve the vulnerable patterns that we detect.
My understanding is that it's really symbolic regression analysis. We're translating the code into data flows and then understanding the data flow from the source through to the sink. Is that a correct understanding?
Yes, definitely. So this whole approach, of course, it does not work on the text itself. So it doesn't work on the text of the code, but we first basically analyze the code and parse it into a abstract syntax tree or basically any kind of abstract tree where we also do some further analysis. And on top of this tree, basically, we can run this analysis and the tree.
Okay. That's a good understanding of how we can determine whether there's a vulnerability. But let's talk specifically now about CodeReduce, because that data flow can be very complex and very lengthy. An input coming from a user might go through 20 or 30 steps before it gets to a dangerous function. And that's problematic, is my understanding. Why is that problematic, the length of that data flow?
Mm-hmm. Yes. So it's problematic for various reasons. The first one is that basically at the end, we want to use machine learning and AI. And of course, the longer the context is, the harder it is for the model to understand. This has always been a problem in the programming languages because, for example, if we can compare it to the natural languages, there it is not the case. So when you talk about something, usually all the things that are close, they are related. But this doesn't have to be the case for the programming languages, right? You might have some function, maybe they are next to each other, but they are not related, or they are actually being called maybe 1,000 lines later. So the model has to basically understand all these long-range dependencies. And of course, this can also happen across different files, right? It doesn't have to be all in the same file. And the model has to understand all these long dependencies. So that's the first and the biggest problem. And the second problem is actually the feasibility of actually running this as a product, because when you have all this information, the model has to process all this information, which takes a lot of time. And very likely the model will then also output something, again, very, very long, which also takes time and money. So this is also problematic, both in terms of the user experience and also the costs.
So one of the things that your team discovered, and maybe it was you specifically, but the group that you were working on, is that reducing that tree aids in the accuracy of the analysis. Is that right?
Yes. So at first it was the whole team, not only me, of course. And well, yes. So what we are doing is basically the following. So we are analyzing the code and we are finding some vulnerabilities. But while we are doing this analysis, we actually also keep track of the derivation. So the derivation in that context basically means why we think something is vulnerable. So we not only say to the users, hey, this is vulnerable, but we also show them basically the flow that we extracted and why we think this is vulnerable. So we thought basically, okay, like since we know this derivation and we can also basically query the analyzer multiple times after maybe we change something in the code, what we can actually do is we can maybe try to filter out the irrelevant parts in the code. And after we do it, maybe we can ask the analyzer again, hey, do you still find the vulnerability? And if yes, okay, maybe those things that we just removed, they were indeed irrelevant. Otherwise, you can always put them back and try again. So we use this derivation and all the taint flow information and to basically create a compact derivation that is still vulnerable, and this can be still detected by the analyzer, but the context is just much, much, much smaller and focused on the vulnerability.
What would be an example of something that was irrelevant to the data flow? Just, I'm dumb, put it in practical means for me. Like, what type of code might you throw away when you're going through that derivation?
Yes, sure. So we can say, for example, maybe I have a file which is written for the purposes of interacting with the database. Of course, there are lots of things such as maybe searching for a user, creating a new user, adding a new user, deleting an existing user. And let's say the vulnerability is actually happens only when a user is being added, a new user is created. So obviously we only need that function and maybe some other metadata in the file, obviously. But all the other contexts or the flow, such as deleting a user or querying a user, they are in that context not related. So neither like I, as a human, when I am fixing it, nor the model, when trying to fixing it, actually has to know about the other interactions with the database. We just care about this particular vulnerability and the other basically related context.
Yeah, so it strips it out. Have we done any analysis on how much of the code on average is stripped out? I know that it's always and it depends on the code type, but is it reducing it by 50%, by 80%, by 20%? Like, what level of optimization is this giving you by reducing the code?
Yes, so that's a great question. And this, of course, depends highly on the type of the vulnerability. But yes, we have done this analysis. So we usually categorize the rules into different categories. For example, we have AST rules. They are basically only matched by using the abstract syntax tree, but not very like complex data flow analysis. So, for example, there it is actually the compression rate is much, much higher because there are more local issues. And for example, there it was around 50x. So it was the whole code was reduced 50 times. If you go to more complex cases, such as like taint flow analysis or the file-wide interprocedure analysis, then it is around mostly 20x. So still a lot, but of course, compared to the ASTs, it's a bit less.
Wow. No, that's super impressive. 50x, even 20x. Is impressive. And so you go from that, you derive it down to just the part of the code that is vulnerable. And then what's the next step?
The next step is, of course, to create an AI model that can basically learn on this data, on this data of reduced code. So, of course, one thing that you need for this is, so basically to train this model, you need both the vulnerable and also the fixed version. So we also use the fixed version, and we basically provide the model pairs of vulnerable and fixed code versions, and they are both reduced. And the model learns on this. And then after that, we can take the model, and during the inference time, basically when the customer or a user requests a fix, we again do the same procedure. We reduce the code, we give it to the model, and since the code is reduced, the model can actually understand it in a much better way, and it doesn't have to learn all those complex long-range dependencies. And then the model also generates a fix. But of course, this fix is also reduced. So the model actually only generates a reduced fix. And then we have some other algorithms in the backend that we use to merge this reduced fixed code into the original file so that we can provide end-to-end fixing.
So it dehydrates it and then it rehydrates it to put it back in.
Yeah.
That's fascinating. And it's clear that we're entering an area where AI is generating the fixes and making these things far easier. Do you worry about hallucinations? I know when people talk about AI and ML that it might generate, well, I have two questions. One is, do you worry about hallucinations? And also, how do you guarantee the accuracy of that fix that you're generating for the end user?
Yes. Okay. Let's start with the easy one, the first one. Yes, of course, I'm also worried about the hallucinations. And I think they are just the nature of how these models are trained. So we talk about intelligence, but I rather like to say it as a pattern replication. And when you do something like statistically, it's just actually tries to generate the text, which is most likely, so to say, based on what it has seen. Of course, since it's just statistics, occasionally, like there is also some bad words, bad tokens, undesired effects. So I think this is just nature of how they are trained, and it will keep happening as long as we do it the same way. So I guess we just have to come up with other ways, such as like post-processing, validating the outputs, and so on, to basically at least to reduce the effects or impacts of these hallucinations. And this is also what we do actually about the second question. So if you just query a model and tell, hey, like generate me a fix, okay, maybe let's say 60-70% of the time it will generate a good one, but what about the other times? So it will probably break your code. Maybe it will make you think the vulnerability is actually gone, but actually in reality it is not a proper fix, it's a partial fix. So all that can happen. And what we do is the following. So we don't trust the model blindly. We collect the predictions from the model, and in fact we query model several times and we collect several predictions from the model so that we can have several candidates and increase the accuracy. And after that, for each of these predictions, we actually rerun our Snyk code analyzer again. And we basically reanalyze the predictions, and then we detect whether the initial vulnerability is now still reported or not. And of course, on top of that, we have also a bunch of other checks, such as the code has to be parsable, syntactically correct, and all these things. So we make sure that the vulnerability that we were initially trying to fix, it is now not reported in the code, and it's also hopefully fixed in the correct way.
That sounds very slow, that it's going through the process multiple times. Or is this taking minutes or hours or days? Like how long does it take to go through that process?
Yes. So on average, it takes 15 seconds right now in production, we can say. But of course, it depends on a lot of factors. So for example, if the initial file size is very, very long, sometimes we get files with 10,000 lines, then of course, the code reduction is actually very, very important, but also it takes a lot of time because it has to reduce all that code and understand it. So yeah, and then once we have this file, we also have to reanalyze it several times. But our analysis times are usually very, very good. So we have one of the fastest analyzer in the industry. So we also parallelize this. For example, I said we generate multiple predictions from the model, right? So all these predictions are actually analyzed concurrently. So it's parallelized. So actually it's same as analyzing one file at the end because we analyze all of them in parallel. But yeah, we do all these optimizations.
Yeah, it's shocking to me. I guess I was leading the witness a bit because I've used the AI fix capabilities and I know how fast it is to come back. Does the model matter much? I know that there are a lot of models out there, and last year I think there was 50 new models introduced, and they continue to come out all the time. Does the model matter in the accuracy and speed of both the code reduction and the fix generation?
Yes, it actually matters a lot. And I think the biggest factor is the model size, basically the number of parameters, right? The more parameters you have, the more matrix multiplications you need to do. And that will basically also take more time. So that's the thing. And on top of that, there is also so-called model architectures, right? The size or the number of parameters is one thing, but you can also combine these basically parameters in different ways. And this is called the model architecture. So right now, there are not many different model architectures. Essentially, I think in the base, all of them are kind of similar to each other. But what sometimes happens is that we actually use these optimization libraries that are also developed by other companies and teams the thing is they don't support all kinds of model architectures. So you might have a great model, but if its architecture is not supported by these optimization libraries, then you will either have to serve it without optimizations or with less optimizations, or you have to basically change to a model that has an architecture which is supported. So this is also important.
What were the comparisons like? I know that we tested T5 and StarCoder and different models in this. Were there some models that were faster and better than others?
Yes, for sure. So in terms of accuracy, so for example, T5, it is one of the early models. It was actually back then one of the state of the arts, but at the time we basically tried it, it was actually slightly getting old because the field also evolves very fast. So T5 was actually one of the ones that performed the worst. It was also the smaller one, so that's why it was the fastest maybe, but the accuracy wasn't great. And then we have, for example, the sweet spots like StarCoder, for example. It comes in various sizes from 1 billion to 7 billion. So 1 billion, 3 billion, and 7 billion. We experiment with both of those. So we realized that, for example, 3 billion is kind of the sweet spot because 1 billion was not performing very well. 3 billion was performing pretty well and it was also fast. 7 billion was maybe slightly better than the 3 billion version, but for that improvement, it was considerably slower. So, for example, these trade-offs are also play a role. And then we also tried Mixtral, which was a mixture of experts back then. It was a huge model. It actually performed very well, but it has around 45 billion parameters. So it was not possible to serve this, although it had the best accuracy and the scores.
Yeah, it's always a trade-off. I know bigger is not always better. Bigger might be more accurate, but time also matters in this and the speed at which it can do the analysis. Do you expect the models to continue to improve at the same rate? If we look forward 5 years from now, will bigger models be faster and better? Or do you think we are about where it's going to be?
Yes. So I think at least initially there will be a trend towards the smaller models because like during the research, basically the simple goal was to get better. So no one cared about the usability, the user experience. It was mostly in the research. And of course, if you could take a bigger model and if you could improve the scores maybe by 1%, this was a great publication. But now it is really starting to get in our lives and the feasibility, the costs, they start really matter. So I think there will be a trend towards the smaller models. And actually, I think currently it's also happening. So right now, mostly the 8 billion is kind of the sweet spot right now. Most models are basically also published with that site, which basically can still do lots of tasks with a great accuracy, but also compared to the others, it's still like servable as a product in the real world. So I think initially there will be this trend towards the smaller models, but later, again, the hardware improvements and all that stuff, if they improve, we can always try, of course, hey, now actually we can also run maybe a 16 billion model at the speed of 8 billion, and yeah, at the end, maybe there can again be some tendency towards the bigger models.
Where do you do your testing? Do you have A100s and H100s at home, or where are you doing your testing?
I wish I had one H100 at home. That will change everything. No, unfortunately, I don't have any GPUs at home. That would be good. It would also reduce my heating costs probably. But no, we use cloud and we use cloud GPUs and we do the testing there. But luckily there, we have A100s, so they are pretty fast. And for the serving, we have sometimes, depending on the cluster, we have either A100 or slightly a worse GPU, basically to save some costs.
Well, it's funny you say that because I often wish I had similar hardware at home, but unfortunately I don't. It would heat my house as well, I think. That the power consumption of the new hardware driving the ML and AI is very impressive. Where do you think this is going? So I know that we're using machine learning and generative AI for the discovery, for the reduction of the code, for the fix of the code. Do you see it being used in other areas of code? For example, do you see generative AI actually creating the code itself? And if it does, is it going to be generating secure code? Where is the industry going?
Yes. So I think the application will increase. So I don't know, maybe not everyone will use it to write code, but at least as an assistant, it will be used more and more. Writing code is a bit, I think, it's a dangerous topic. So I don't know, for example, from my experience, if I ask it to do something, it's usually like in the right direction, but it cannot be used as it is. This is, of course, I'm saying this like while I'm putting the security concerns aside, only like from a functionality and the correctness point of view, even there. So of course, like, I don't know, if you want to write a function that detects whether a number is prime or not, this is easy. You can take it as it is. But once you start actually doing more complex tasks, I don't think it's yet there. And regarding the security, we have actually benchmarked this. So one other engineer in our team did this, and like security is not even a concern for the generative models right now. So most of the time, the generated code is very simple and just basically focuses on the essentials, but without the security concerns. So we found a lot of vulnerable patterns, vulnerable code, and if you use that code as it is, you will have lots of problems.
Yeah, I saw that. And actually, one of the things that was interesting is the newer models were generating less secure code. And in fact, Gartner just came out with a Magic Quadrant for coding assistants. And there's two statements that were interesting. One is they said by 2027, 90% of engineers will use a coding assistant, which was interesting. But it said 25% of software vulnerabilities would be created by that AI generated code. So that's kind of scary. And so it's good, I guess, that we're thinking about how to use AI for the guardrails and securing that code, which is what you're working on. What gets you most excited? So when you think about the future of AI and ML, I wish I knew half as much as you about this world, but what makes you most excited about where we're going, what the future holds?
So I think the most exciting thing is that it will basically allow us to do maybe more complex things, because it will automate the simple tasks. And now we as the human, we can actually focus on the more valuable things. And we can actually also build these ideas and all these products actually much, much faster. So I think the efficiency and automating the simple and the burden things is, I think, the biggest impact. And this is, I think, the general. And the personal one is, of course, I am very excited about AI Fix being used by our customers and by developers. And I think hopefully this will also increase. I'm also excited for this. And as you said, so the AI will be used to generate code, but other AI models will be also used to basically fix those codes. So we are kind of basically going to a world where AI models kind of actually interact and do the job among themselves.
Yeah, I'm interested in the world where the generated code isn't even insecure, that we use AI even before the code gets generated, but that's probably a topic for another day. If you could take AI and automate one part of your job to make you more productive, what would you use AI to do?
Okay, that's a good question. I would use my right to help actually my teammates, and that's not my day-to-day job, but we have lots of customer tickets, basically requesting some features or maybe like asking questions and all that stuff, or maybe installing Snyk and all these things. So I think they take some like significant time for us. Of course, it's very valuable work. It has to be done, but I think this is also something AI can help. And then we can also focus on, again, doing the more features and better analysis, faster fixing, and all that stuff. So I think I would automate this part.
Yeah, that's fantastic. AI, I look at it as an assistant to make us more productive, more efficient, to focus on the things that we really want to focus on. Well, Berkay, it was great to have you on and to explain to our audience how CodeReduce works. Congratulations, by the way, to you and your team. It's a fantastic step forward in the industry, and it truly highlights how Snyk is a thought leader, but even more importantly, we're thinking about how we help our customers in meaningful ways. So thank you for sharing, and thank you everyone for attending the podcast today, and we will see you next time on the next episode of The Secure Developer.
Yeah, thank you.
Thanks for tuning in to The Secure Developer, brought to you by Snyk. We hope this episode gave you new insights and strategies to help you champion security in your organization. If you like these conversations, please leave us a review on iTunes, Spotify, or wherever you get your podcasts, and share the episode with fellow security leaders who might benefit from our discussions. We'd love to hear your recommendations for future guests, topics, or any feedback you might have to help us get better. Please contact us by connecting with us on LinkedIn under our Snyk account, or by emailing us at thesecuredev@snyk.io. That's it for now. I hope you join us for the next one.